Welcome to this presentation on converging and diverging nozzles. This is in the sequence of compressible flow. If you haven't seen the other presentations at this point, might be worth going back and checking those out first to understand what we're talking about here. If you want the handout that goes with this, please check the link in the description, and that you can follow along with that. Here's where we're at in the overall course, applications of thermodynamics. Is a compressible flow underneath the power systems. It kind of goes along with gas power systems, and you can see what we'll be getting onto in the future. All right, so let's get into it. We looked at this example last time in one of the previous lectures, and so we're doing an analysis of looking at basically our stagnation calculations. What was temperature, pressure, density, and other calculations we had at 1400 kilopascals, at 1200, at 1000, et cetera, as we move through here. Now, as you can see, there's an overall shape here of a converging, diverging shape. And let's look at the data we got from that in chart form here. And we saw overall an increase in the Mach number with position along our nozzle. We also know the area decreased as well as increased as we moved along. And the thing I want to note about that is if you notice right here, we have the Mach number at some area, and then if we move across here, I can draw a relatively straight line. All right, we have about the same area, but notice the Mach number is way up here. All right, so the same area, we can have different Mach numbers, all right, all depending on how the flow is going through our converging and diverging nozzle. All right, so that's really important. And we kind of looked at that last time. We're going to look at that more in depth here today. All right, so if you take the stagnation ratios that we had from one of the previous lectures and you combine them together, you can come up with a relationship between the area, given area that we're at, divided by the area at the throat. All right, and the throat, as we noticed before, is the transition point. And what you can see here is when these two are equal to each other, that's obviously equal to 1. The ratio equals 1, and that occurs when the Mach number is 1. All right here. All right, when the Mach number is 1. So we have the sonic case right there at the throat, and we have subsonic over here. Mach number is less than 1, and over here, I can line all the way up here, we have Mach number is greater than 1. All right, so at the same area, again, highlighting before, the same area, we can have different Mach numbers depending upon different conditions that are there. But the only way we can get to these supersonic cases is we have to go through the sonic case at some smaller area. We have some converging nozzle at subsonic speeds and a diverging nozzle at supersonic speeds in order to get to those higher Mach numbers. All right, this relationship extends to other things as well. We can see here different areas. Again, here's the one where they're the same right at the throat. And in that case, the pressure, right? So the pressure at the throat versus the stagnation pressure, that ratio is 0.52828. And the temperature at that point versus the stagnation temperature is 0.833. And again, you notice that where the Mach number is equal to 0, i.e. stagnation, that's the highest possible we can have. So we have the temperature at stagnation is obviously equal to stagnation, but everything else here just goes down as we move through our nozzle. All right, you see the Mach numbers here continue to increase from subsonic into supersonic Mach numbers. And again, we notice the area is 1.18, for example, there, and 1.18 would be somewhere in here. All right, so we get the same areas, all right, but different Mach numbers, different temperatures, different pressures as we move through. So how do we get these different values? How do we move from subsonic into supersonic through this converging, diverging nozzle? Well, let's look at that. All right, so overall, these are the different shapes that we looked at before. So if we just wanted to do subsonic flow and get up to sonic case, we would do our converging nozzle. If you wanted to get to supersonic speeds, we now know that we have to move through a converging, diverging nozzle. All right, so let's see how that works. So a lot on this information here, but I'm going to step through it really slowly. What we see here first is that we have some pressure upstream. So before we enter the nozzle. Actually, I'm going to shift over to laser pointer. So we have this basically stagnation case. Velocity is approximately 0 before we enter. We got some stagnation pressure and stagnation temperature. Going to the other side, this is the pressure right at the exit of our nozzle. And then we have some back pressure. You can consider this the atmospheric pressure. But what they're showing here is they have some valve. We can adjust the back pressure that exists right here, not at the exit, but maybe a little bit beyond it. But again, this would represent if we had an engine taken up to altitude, this would be the atmospheric pressure. So you can think of it more like that. So what we're showing here in the first line is in the first case, case A, is where the pressure that we have upstream of the throat and the pressure downstream of the throat all equal each other. All right. And in all these cases, except when we get down here, the exit pressure and the back pressure are both equal to each other for all these cases. So just heads up with that. All right, so if there's no pressure difference, so the downstream pressure is the same as the upstream pressure, nothing's happening. Nothing's moving. There's no pressure driving the flow. So we're just constant pressure the whole way through for case A. For case B, what we do is we open up this back pressure, and so we drop the back pressure just a little bit. And what happens is the exit pressure is still the same as the back pressure. But now there's a pressure difference. It's actually going to draw the flow through. And so we see the flow is going to go through. As it goes through the subsonic nozzle, the speed increases. All right, the pressure drops, the speed increases. After it goes through the throat, it works as a subsonic diffuser and slows down. The pressure increases to the exit pressure for case B. Case C, we drop the pressure outside a little bit further. So now the pressure goes down a little bit further. Velocity goes up as well, a little bit higher, and it continues to increase before it gets back to the exit pressure. In case D, what we've done is we've dropped the pressure outside such that the pressure drops to the critical pressure, the pressure of the throat, where we get Mach number equal to 1. So we reach sonic conditions right at the throat, but then again, there's not enough pressure to go supersonic, and we continue to go through a subsonic diffuser before we get to case D. All right, so now we get to the interesting part. Case E, we've dropped the pressure even further at altitude, let's say, the back pressure even further, but the back pressure still equals the exit pressure. All right, check out what happens. We go through our our subsonic nozzle. We increase to sonic, and it actually works into the, goes supersonic. The Mach number goes greater than 1. And we go through part of the nozzle before we get to this normal shock. So what happens is there's not enough energy in the flow to make it the whole way through our supersonic nozzle. All right, and so we have a sudden compression of the flow that goes across the normal shock. We go to a higher pressure, and we go through the what's now a subsonic diffuser up to case E. All right, for case F, now we drop the exit back pressures even further, even lower, and you can see the pressure drops down to a sonic case, pressure continues to drop, Mach number is now going supersonic, and the normal shock happens, compressing the flow before we go back as a diffuser to point F. Now, what I want to highlight here is note that for case E, F, and all the ones that happen here further, this region right here for case E, and then for case F, for the future cases, and then all the cases to this point. But just for case E, let's just compare case E to F here. Both case E and case F do this. They do the exact same thing. So what happens here when we go into compressible flow, the upstream case, right? The upstream has no idea what's going on, right? If we go to where we're supersonic, it looks like if I would change the pressure between E and F, everything upstream of the normal shock sees no difference. All right, and that's what the compressible cases do to us. Notice how when we move from A to B to C to D, things changed upstream at any place. So you can go along here where we're going through the subsonic diffuser, up here through the subsonic nozzle. Everything changes for each case A, B, C, and D. When we get cases E and F, things do not change upstream of the normal shock. All right, so that's a key thing to keep in mind as we look at compressible flow. Things will not change upstream. The information can't make it upstream. All right, and we'll look at this more in some other examples as we move forward. All right, dropping the pressure further from E and F, we're now at G. And G is the last case where the exit pressure will equal the back pressure. So that's what it's showing, like this solid line going across, because now the pressure drops, we get to sonic conditions at the throat. It continues to drop, and now we're supersonic, going through a supersonic nozzle all the way till we get to the exit. And at the exit, there's a normal shock that suddenly compresses the flow up, so the exit pressure, or the pressure just after the exit, equals the back pressure. So that's case G. When we go on to case H, now we're going to have a oblique shock wave. Oblique shock wave that gets us up and compresses us up to the back pressure. That case I is a very unique case where we've gotten the back pressure down to be just the same as the exit pressure, so there's no shock that's occurring at all, but obviously it's very perfect conditions for that to happen. In a case J, where actually the pressure is lower than whatever's happening, the pressure at the exit, and so we have an oblique expansion wave expanding down to the lower pressure. Right, so let me give you some examples of these. So here are some examples. We have the SR-71 Blackbird with its overexpanded nozzle, and the Bell X2 with its underexpanded nozzle. And the way these work is if you scroll down the page here, you can see the overexpanded nozzle. And what's neat is you can just hover over these things and it'll show you and obviously give an explanation about what's going on here. But you have this oblique shock that forms at the exit. All right, so if the pressure at the back pressure is a little bit higher than the exit pressure, you'll have this oblique shock that forms. And it says the flow that has passed through the shock wave will be turned towards the center line. All right, so that's this region here that's flashing. It gets directed toward the center line, so you can see there at 2, going up toward the center line, and then it reflects back and forth. But that initial direction toward is what keeps it from not billowing outward. Whereas down here for the underexpanded nozzle, you can see there at 4, it goes outward right away. And this is due to these exhaust gases expand via Prandtl-Meyer expansion waves, right, turning the gas outward. All right, so as it exists, the oblique shock waves bringing them toward, and the Prandtl-Meyer expansion waves putting them outward causes that billowing effect. So this website also shows some, basically the same picture of the XR71, but gives some other explanation as well. So that's the other link on the slide. I'll put links to both these websites in the description. All right, so again, here's the overexpanded nozzle. So this one's kind of a zoomed in a wind tunnel type testing. So it looks like it's billowing, but it's staying relatively compact, right? And you can see here with this jet fighter, again, a nice narrow overexpanded nozzle. But with the underexpanded nozzle, here's Apollo 11, high altitude, low pressure outside, so you're going to get this underexpansion that happens and causing it to billow outwards. So typically we don't see the underexpanded, we see the overexpanded case. All right, so we'll do this example in class, but just to give you a little bit of heads up what we have. We don't necessarily know much about the shape. We just know we have the Mach number of 0.2 coming in. Temperature at the inlet is 595 degrees Rankine, a pressure of 77.8 psi, a mass flow rate of 1 pound per second. We know at the exit we got a Mach number of 1.5. So it has to be converging diverging. If you come in with a subsonic flow and you're leaving with a supersonic, the only way you can do that is a converging diverging nozzle. So we'll model this with air as an ideal gas using a specific heat ratio of 1.4. All right, we want to look at the stagnation pressure, find the stagnation temperature, and let's find the throat area. What's the area here at the throat, and the exit area as well. So we'll do that in class, and thank you for listening.